Now, if I just would have did work.
Doing work is slightly important to getting a good grade. It does help.
Oh, I spent 2 hours doing the goddamn.
Oh, all right, so we're going to talk about vertical asymptotes first. Then we're going to look at horizontal asymptotes because our ultimate goal is, remember, you want to be able to graph a rational function by the end of next week. So our asymptotes are imaginary lines that our graph cannot cross. So an asymptote, come on. An asymptote is an imaginary line the graph cannot cross. So here, our asymptote is shown by this dotted line, and whenever we graph our asymptotes, we use dotted lines just to kind of show, like, we can see where it is, but we know that it's not actually part of the graph. It's just kind of like, remember when we graphed piecewise functions and we drew our fences to kind of show us where our graph was switching from one function to another? Same thing. It's like showing us where the graph is breaking from the first part to the second. And when I look at my graph, I see that it has 2 pieces. This part of the graph will get really, really, really close to that dotted line, to that asymptote, but it's never going to actually touch it, and it can't go over it. This side would get really, really close over here, but same thing. It's never going to actually physically touch it, and it can't go over it. So when we're looking at our vertical asymptotes, these are x values that cannot exist in our graph. So this graph that we're looking at right here cannot have an x value of 1 because my asymptote is at that x value of 1. So these asymptotes help us figure out where our graph can't be, so then we know everywhere else that it can be. Our asymptotes also only show up in rational functions. And a rational function, its fancy definition is f of x equals p of x, so some other function over q of x. So it's basically our big fraction functions. Where p of x and q of x are functions and q of x does not equal 0. So that's our mathematical way of saying it's going to be our functions that look like fractions. Which you saw, the most basic form of this is the 1 over x that we looked at with the parent functions. But now we're going to get even fancier and look at all different versions of fractions. Everybody's favorite. Yay. So, if we want to find a vertical asymptote, which is what you're going to be asked to do, the first thing you want to do is factor the numerator and factor the denominator completely. So 1 completely factor numerator and denominator. If possible. So it might not always be possible. There might be functions that don't actually have things that we can factor. Like there's just an x in the numerator. We can't factor that. It's already as simplified as possible. But if we can factor and if we can simplify, we want to. Because sometimes we may end up with the same factors in the numerator and the denominator, which then we can cancel out, and that will make solving easier. So then step 2 will be cancel any factors that are the same in the numerator and denominator. And remember, numerator is the top of your fraction, denominator is the bottom. So once we've simplified it as much as possible, we've canceled anything that's exactly the same in the top and the bottom, we're going to take whatever's left in the denominator, set it equal to 0, and solve for x. So set remaining factors in the denominator equal to 0 and solve for x. Once we solve for x, those x values will be where our asymptotes are. So we'll show you this with some actual numbers so it makes a little bit more sense. So we could say, find the vertical asymptote, or possibly asymptotes. We could have more than one, because like we saw in the do now, there were some equations that had more than one x value for an answer, so we can have more than one asymptote. So we want to find the asymptotes of f of x equals 2x over x squared plus 1, and then we're going to use our asymptotes to state our domain. So the first thing I want to look at is I want to look at the 2x and say, is there anything I can factor out of 2x? Is there anything I can simplify there? And there isn't, right? Because it's just a 2 and it's an x. There's no common factors there. There's nothing going on that I can simplify. X squared plus 1. Nothing going on there that I can simplify. Let's actually, before you write this down, change this to an x squared minus 1. Do you remember how to factor x squared minus 1? No. That's the difference of perfect squares. Does that sound familiar? Yes. So difference of perfect squares says difference means subtracting, and I'm subtracting two perfect squares. X squared is a perfect square, 1 is a perfect square. If I was going to factor this, 2x, there's nothing for me to factor. But x squared minus 1, I can make x, and then I just take the square root of 1, which is still 1, and one of them is positive and one of them is negative. So now once I factored it, I want to see if there's anything in my numerator that's the same as my denominator. And here I can see there's not, right? I have a 2x. Then I have an x plus 1 and an x minus 1. If any of those factors were the same, I could cancel them out and completely get rid of them, which just makes solving easier. So that's why I want to factor to check if there's anything I can get rid of before I try and solve something really complicated that I don't have to. Since there's nothing that I can cancel out, I'm going to take my denominator and set it equal to 0. So I'm going to take my x plus 1 and my x minus 1 and set it equal to 0. Once I have two factors set equal to 0, I set them both equal 0. I can split them up and say x plus 1 equals 0, x minus 1 equals 0. And then I can just solve both of them. I subtract 1. I get x minus equals negative 1. When I add 1 over here, I get x equals 1. So my vertical asymptotes are at x equals negative 1 and x equals 1. So my vertical asymptotes x equals positive or negative 1. Which means if I were going to draw a graph if I were going to actually graph this, or I were going to start to graph this, vertical asymptotes at positive and negative 1 mean that I have an asymptote here, and I have an asymptote here. So my graph is going to have 3 pieces because I'm going to have a piece of graph over here, I'm going to have something going on in here, and something going on over here. But I would see, when I was looking at the graph, I would actually see a physical space at negative 1. There's just going to be like an empty floating around space where the graphs aren't going to touch negative 1, and I'm going to see a space at 1 where the graphs aren't touching. This is mind-blowing for a Monday. We're gonna make it less mind-blowing, I promise. So now if I'm looking at this and they're asking me to state the domain of the graph, the nice thing about the asymptotes, or the asymptotes tell you everything that x cannot be. So if I want to say the domain for this, the only values I cannot have in my domain are x equals negative 1 and x equals positive 1. I can have every other number. So when I write my domain for that, I'm going to say, okay, I can start at negative infinity. I can't have negative 1, so I'm going to skip over it. But then I can have everything after negative 1 until I get to 1. Skip over 1, and then keep going. So my actual asymptotes, my 2 answers for my asymptotes, tell me where to split my domain. So because I had an asymptote at negative 1, I have to skip over negative 1 in my domain. And the way I skip over it is by saying, okay, go up to negative 1, close the parentheses, and then start again after negative 1. Then I want to skip over 1, so that's where my next interval comes from. Want to see another one? Yeah. Spice it up a little bit and say, find the vertical asymptote for x minus 3 over x squared plus 2x minus 15. So the first thing I have to do is see if there's anything I can factor. X minus 3, it's got nothing else going on. There's nothing I can simplify there. There's no like terms. I don't have any big exponents I can split up. The numerator is taken care of, but my denominator I can factor. My denominator I can say, okay, what multiplies to negative 15 and adds to 2? 5 and negative 3, right? So that means I have factors of x plus 5 and x minus 3. Ooh. Do I have anything that's the same in the numerator and the denominator? Yeah. The x minus 3's, right? So I can cancel these x minus 3's. When I do that, though, I need to hold my numerator's place with a 1. So I can't just get rid of the fact that this is a fraction. Even though I've canceled everything out of the numerator, this fraction now becomes y equals 1 over x plus 5. So I can't just eliminate the idea that there was a numerator there entirely. I have to still have a numerator. But because everything's gone, I'm just going to hold its place with a 1. So now I've simplified it as much as possible. So now instead of having to solve x squared plus 2x minus 15 equals 0, I only have to solve x plus 5 equals 0. Which, did you ever think you'd see the day again where you had to solve a one-step equation? This is like back in the glory days of Bolger. X plus 5 equals 0, which means x equals negative 5. So you have a vertical asymptote at x equals negative 5. Which means if you were going to graph it, back negative 5, 1, 2, 3, 4, 5, you would have your asymptote would be at negative 5, so your two pieces of your graph would be on either side of that. Which all you have to be concerned with today is being able to physically draw a dotted line at that x value on your graph.